Okay, I'm going to talk to you about some more about 1.5, the quadratic applications. I'm going to be talking about example 3. So if you want to find that in your book and follow along, that is on page 126. So you will find a formula that we use a lot in quadratic applications, which is the height of a projected object. So as it turns out, all projected objects, basketballs, baseballs, rocket ships, whatever, they start, at a point maybe on the ground or at a certain height off a building or whatever, then they project up and they have to come back down. So we have a path they follow, which is always going to be a quadratic equation, as it turns out. Our quadratic we're studying shape. What we do in the next chapter is we actually graph. So don't worry about the graphing yet. Right now we're just talking about it as an equation. But I would like you to, start, at least realize it does have a picture that flows with each type of equation. So, and it's kind of neat here because it's an application we can relate to, objects going up in the air, then they come down. My figure's not perfect here, but should be symmetrical. They go up, hit a high point, and then come down at a symmetrical looking shape called a parabola. Either a downward parabola, we also have upright parabolas we'll study. But those all are applied from the quadratic. So the formula given at the top of the page is the height of an object is always, and this is measured if it's feet per second. So if you take a physics class, you all may do it in meters per second. Our algebra book does it with feet per second. So don't worry about that. That's always given in the problem anyway. But there's a negative 16 t squared. T being the time after the object is projected. So this goes up in the air after 1 second, 2 seconds, or whatever, depending on how fast it's going. But T is the amount of time that passes, T for time, right? S, though, I don't know why that's S, but that's the height of the object after these amount of seconds. So after 1 second, you can crunch your quadratic. That tells you how high it is, and so on and so forth. V sub 0, when we use this sub 0 like a subscript, that means that's the initial something. You'll see that along in our book as well in other applications, but the sub 0 means here's how it started out, the initial, in this case, velocity, how hard it was thrown. We know that's a factor in projected objects, is how hard is it thrown. So that's velocity. S of 0 stands for the initial height. Were you on the ground, then the S would be 0. Were you on top of a building throwing something into the sky, or on the mountain, whatever. So that's how high up, and that's always given in the problem. These aren't things you'll have to derive some way. It will be given. For example, on example 3, they give us an equation. This one must have been projected from the ground because there's no S value on the end. And 100 would be the velocity, 100 feet per second. What you might wonder, why is the negative 16 there? And that has to do with the pull of gravity. So that is already factored into the problem. So all we have to know really on these is understand that T is time, after how many seconds. S is how far up it is from the ground, the height. S is height, T is time. I think T is time makes sense, but this S is height you may have to think about. Anyway, our question is, and to give it more perspective, I should read your example 3, which says, if a projectile is launched vertically upward from the ground, that's why again you have a 0, no number there, with an initial velocity of 100 feet per second, so that's already factored in, neglecting air resistance, its height S in feet, that's here the height above the ground, after T amount of seconds is given by, and they give you the equation. So we don't really have to derive our own equation. So then we have 2 follow-up questions here. Question A is, after how many seconds will it be 50 feet above the ground? So notice our clue is after how many seconds. We are looking for time. We don't know time. We won't be able to fill that in. An easier question, which they didn't ask us here, would have been, how high is it after 1 second? After 1 second, I would have put a 1 there, a 1 there, 1 squared times negative 16 would have been negative 16, plus 100 times 1 would have been 100. Let's see, what is that? 84. It was 84 feet above the ground after 1 second. So that's more arithmetic. You could figure it out if you knew time. Like after 2 seconds, you could plug that in, work that out. That'd tell you how high you were after 2 seconds, 3 seconds, and so on. Eventually it has to come back down to the ground though, but there's some highest point it reaches, then it starts coming back down. So you could plot that and figure that out, but again, we're not quite doing that, just kind of getting that mind in your mind there. But our question is a little tougher. It gives us a quadratic to solve because we don't know seconds. We know 50 feet above the ground, so that belongs in for S. So to work this problem, I'm going to change S to 50 and solve for T. And then I've got a quadratic now to solve. So to solve a quadratic, we know that we get it all on one side equal to 0, get it in standard form, and then we can use the quadratic formula or try to factor it if it's factorable. So we'll solve that in a second. But let me go ahead and set up part B. They could have done that, asked this question all day long. Well, how about 60 feet? How about 70 feet? Well, how about 2 feet? So that we could work many variations of this same problem, plugging in different feet amount. The other question, though, that was in the book, the example is, how long for the projectile to return to the ground? So this question does come up a lot. A common question is, how long does it take something to return to the ground? So what we need to do there, if we're on the ground, our height above the ground would be 0. So that means plug in 0 for S. So when S is 0. So we'll do the problem again on B part with a 0 there, which is a little easier for us. So we'll do 0 equals negative 16t squared plus 100t. All right, so let's go ahead and talk about this A part. To work A part, I would probably, to keep the numbers positive, I'd go over to the left side to bring all my terms this way. 50 was already there, equals 0. Standard format. And if you could reduce, now you don't have to, but it gives you the same answer whether you reduce it or not. So anytime you have an equation with fractions in it, especially, you'd want to clear your fractions before you try to work with it, because it's all, you'll get the same answer. Any reiteration of this, any multiples of this is the same ratio answer. So if you want to divide by something to make it easier or multiply by something to make it easier, the ratio stays the same, and so the answer works out. So on this one, I know these are all even numbers, so I could at least divide by 2. I think that's the best I can do, though. I could divide both sides of my equation by 2, and then I'd have 8t squared, 50t, 25. 0 divided by 2 is 0. Let me get that one out of the way. So that helps a little bit, right? So, but that's optional. Now at this point, I would probably try to factor it because I like that method first, and I sometimes get the answer quickly and I don't have to use the formula. But anyway, I'm looking at your answer key, and I don't think that it actually is factorable. So I might try to factor it, but I couldn't get it to factor. As it turns out, it's not even factorable. So I do need to use the quadratic formula. So A is 8, B is negative 50, and C is 25. I'll plug that in my formula, and I will have, let me move some space here. So plugging in the formula, and we know the quadratic formula looks like this. It works for any quadratic equation. And I'd plug in the negative of B, which is going to make it positive 50, plus and minus, B squared, which is negative 50 in parentheses squared, minus 4 times A times C, all over 2 times A. A was 8, wasn't it? 8. So then I'm going to use my calculator. I would probably do what's in this parenthesis first and get that number calculated. So 50 squared, negative 50 in parentheses, squared, minus 4 times 8 times 25 is 1700. So I've got 50 plus and minus to get the two answers, 1700 over 16. Now we talked about how we like perfect algebraic answers. Normally that's preferred, but if it's a reading problem, we would like to know really what is this equal, we'll go ahead and get a decimal approximation. And your directions should tell you if that's okay or not. So definitely on this, we want the real answer, like a decimal answer, to get an approximation how many seconds this looks like. So algebraically, I would say that's 100 times 17 and reduce my radical. But again, since it's a reading problem, I'm going to purely punch on my calculator. 50 plus the square root of 1700 equals divided by 16, and get a decimal approximation for that. So let's check that out. That should give me 5.7019. Again, because it's a radical, it's not going to be a perfect answer when you do a decimal, so you'll have to round to some place value. Let's see if this problem said specifically what to round to. It looks like 2 places. So I would go out 2 places. The 1 would not round that up. So 200ths place or 2 places, that'd be 5.70 seconds. So that's how after the to get to 50 feet, 5.7. Now let's see what happens when I do minus. 50 minus square root of 1700 over 16, because there's 2 answers there. We'll see how that works out. And 0.5480. All right, so we did get 2 acceptable answers, and we'll talk about why we would have 2 answers. But when I go back 2 places, the 8 would round that up to a 55. So 0.55 seconds and 5.70 seconds are the 2 answers. So again, why would we have 2 answers? And it goes back to this picture I drew on the top. Whenever something is projected up in the air, it reaches a highest point and it comes back down. Well, ours was saying at 50 feet. So, I mean, I haven't drawn it to scale or anything, but let's imagine this was a graph, and I don't know, maybe there's 50 feet up, the y value 50 feet. So after how many seconds, seconds being the t value this way, again, we're not really graphing, but I'm just getting you thinking about it. After, say, how many seconds, it says, is it up 50 feet? So there's 2 points in time that is actually at that height. It goes up a little further maybe, and then it comes down, it hits 50 feet again, then drops down to the earth. So there could be 2 solutions to these because of that. There's 2 points in time, just like half a second and 5.7 seconds, that it's up 50 feet in the air. And so that's why that would make sense.